So welcome back to another video. Just going to do a short video for you to show you my progress. And now it's getting a bit difficult because and I can't see under the metal layer. So, and also I've been in contact with John, which did this dieshot, and I'm sorry to say, but it doesn't have time. So I'm just going to refer to the first and the second video. If you have questions, I probably have answered those already there. Right, so what I did in the beginning, just to recap, was to find the address lines, which are green and orange, as you can see in this C shape. And then they have the data signal, which is purple. And those goes around here as well, and also into the middle. And then from this address and data, we could find the address decoders. So the address decoder is, as you guess, in this C shape. I can quickly show you how that works. So let's take one of these registers, for example. I just want to refer to you to the other video if you want to see how that works, because I've explained it very carefully there. So, but as a recap, what you basically see, why you have to see the other video. But whenever there's a negated, you say 1, so it's the opposite. And whenever there's a non-negated, you say 0. So here you can see the connection. So this is a 1, 1, 1, 0. So this is register E actually, and connected together with the read and write strobes. They have an output here, which then can enable either a read into the register or a write. So I have now done that for all of these to find all these read and write strobes. And this is what I come up with. So here we found all the timers, timer A and timer B. We have the serial shift register, the interrupt control register, as we saw the last time, and then you have time of day down here. And then you have data port A and data direction, which is just behind it. You can see the port on the side here, PA0 to PA7. PB0 up to PB7, so that makes sense, having the data port next to the pins. So I got a question on Twitter when I posted about this, why the time of day module is so big. Well, in a real-time clock that you can get nowadays, it's usually just a 16-bit register that keeps time. And up here you can actually see your 16-bit registers. You can see the low byte and the high byte, so let's just turn it off for a moment. You can see we have 1, 2, 3, 4, 5, 6, 7, 8, and then you have another one here, so that's 16 bits. And down here it's different. And why is it different? Well, it's a binary coded decimal system. So one digit is going for 0 to 9, not 0 to F. So that means they have decoded every digit. So let's just look at hours here. And you can see in the 24-hour clock anyway, you have the first digit goes from 0 to 1 to 2. So therefore you have 3 bits. I think maybe that's here. I can't really see it, but here the second digit is going from 0 to 9. So therefore you need 4 bits of those. And over here, yeah, you have minutes. And the minutes goes from 0 to 5, like 59, you know. So therefore you need 3 bits, so you can get to 0 to 8, but you just need 0 to 5. And so on. So here it goes to 9, and then it goes to 5 again, as you can see, 3 bits, and then it goes to 9. And then you have tenths, so this one just counts to 10. Right, so you need 4 bits. So it's kind of wasteful in that way. You kind of waste a bit for every digit here. And they also need a lot of logic just to find out that you are at number 59. So I haven't found it yet, but I think there are some comparators in here. And then it will just trigger an enable count enable on the next digit. So yeah, so that takes up a lot of space, and if you would compare it, the time of day would have been like 40% if it had been a 16-bit counter. So yeah, but and why would you need that? You probably wouldn't. If you're going to keep time, you just need something that counts. You don't have to convert it on the fly. Just this conversion can be done in software, and you don't convert every second, you just convert every time you need a clock, right? So that could be every second anyway. So yeah, so but now the other things I've looked at, I've started drawing contact and pulley, and it's not so easy, but it's starting to get somewhere. For example, you can see the clock comes in here, and there's several inverters going on here, so it's inverted once, and then you can see this is just one big transistor which is divided in two, and the reason why they do this is because I think they don't want such a big pull-up, because that will be wasteful, right? If you have a low level, signal is low, you will have a drag into the pull-up, but since it's small, it doesn't do very much. However, the output of that pull-up is amplified here, sort of. We can just have a quick thought experiment here. So if the input is high on the clock, it will pull this one to ground, right? But it also pull the pull down to ground. Therefore, the line here, the pulley, will also be at ground. So instead of having this large transistor here in a large pull-up or a hard pull-up, it just turns off basically here. So it's an amplification. And you can see this transistor is just much larger, so you get the same signal again as you had to begin with a little bit of a propagation delay though, but that's okay. Probably, I hope. Then I basically think they're doing the same once more over here. So they not sure what's going on in here. If they are doing some sort of two-phase clock thing going on, but what you could see from this clock here, which was amplified, we can actually turn on a doodle here and follow it around. So. And it goes down to the control signals, and I think we should look a little bit about the control signals, chip select and read write, because they are very important for this chip. As you saw when I decoded the address decoders, we always have address, and we also have control runs for read and write, and those read and write lines, they go like all over the chip. So you can't just have a small transistor, you need amplification for that. And reason why I say amplification, you can't just take a signal and drive a large transistor. You probably need to, yeah, you have to amplify it in several stages often. Or that's what I see. I don't have the math here, so you can see chip select and write. Those two. Chip select is blue, read write is orange. Let's focus on this area. We can see chip select goes in here, and we have a clock, which was the red line, coming in here, and this is ground. So basically one of these two can pull this net to ground, and this net in the middle. And then you have here, which is something coming from like an inversion of read or write here. I think I don't know really why it does it yet, but basically what it does, it has a pull up here. It can invert read or write, so you have revert inverted, and it looks to me that this, if I turn off pulley now, that these are just two pull-ups connected together somehow. So it means that this signal is the same over here as over here. So therefore you have read-write inverted over here on this line. That's why I have this equation. So and then you get the equation. When you have all the transistors on the network, then you can draw the equation. So the equation is basically, this is a wired OR connection, so you have chip select here, so you have that, or read-write inverted, that was this line, and then you have a clock. So basically what we do then is do the De Morgan, which basically just inverts all these symbols, and then you will have to change the operator to an AND. So therefore you get read-write or AND, chip select not, and clock not. When that condition is met, you will have a signal that looks like that. So basically you have a read signal with a chip select which is active and a clock which is low. Then you will have something happening here. And you can see this pull-up is special. It acts also as a connection to the next stage here, which I haven't really drawn up yet, but I think it goes over here. I'm not sure yet where this goes. I really hope that I will find that soon. And it's a bit convoluted here, but everything that happens here is basically the same. You have a chip select and a read-write, and then you get some sort of read-write signal. And I was also talking about amplification, and you can see it's just the same signals that are produced here. It's just going into another really big transistor over here. And therefore you get the output of that big transistor is then just going out in the chip all over the place. So you can follow it around, this blue and the cyan. You can see it goes down here. Yeah, so it goes everywhere. So yeah, so that's what I've looked at. I also started looking at the clock. So which is interesting itself. I wonder if it's a two-phase clock overlapping, so hopefully find something interesting. Oh yeah, that's why I talked about the E register here at the beginning. I show you the address decoder for E. If you want to know how you decode this, just look at my first or second video, and then you will see how that works. However, I wanted to see if there was some connection between if you look at this document and for the CIA, the wiki, C64 wiki, on register E you have bit number 6. There's a serial pin. It could be input or output depending on that bit here. And the serial port register or serial shift register is at C. So let's see if there's some connection between there. And there is. So let me just show you quickly what I found. So we have E up here. And then you have the C register down here, the serial shift register. So what I was looking for then was bit number 6. And that's the data bus, the second from the top there. As I told you before, these purple lines are data bus lines. You found that this is E, so basically this is 1 1 1 0, which is E, produces these two guys, and they go all the way up here. And then I also found it also hooks off the second, yeah, there you go, the second from the top, which is bit number 6 on the E register, which is this, input output serial port pin goes into here, and it has something to do with this control signal, so I'm confident that we are in the right place. And I was looking for an output of this. I don't know exactly what's going on, but it's a register, and the register will have an output. So we could see that something is, if I turn this doodle off, something is going out here into a wire here, and then diagonally here. So let's try and I have drawn it in the doodle layer there. So let's just follow it. I can show you. Oh, there it's tapping off already. What is it doing? Yeah, so it basically acts like an enable for this large output driver. And you can also see this, you don't have to disable an input, but you have to disable an output driver. So here you have to see the input of that pin, serial input output. And if you also, it has, I think it taps off in two places, like there and there. And then it has another one here, and this is for the count pin, which also needs to be controlled. So this serial port works in that way that the data is put on the serial port pin, and then it is clocked with the count pin. So, and if it's an input, the device driving this chip needs to control these two lines. And then I was also interested, where does that line go further? Because it doesn't have to only enable those two pins, it has to also interact with the registers. And fair enough, it actually splits up here into here, and it also goes further into here. And yeah, there you go. There's your serial shift register. Maybe it's not rectangular, maybe it goes up here as well, I don't know. So we probably need some logic for the input. So, and yeah, so I just wanted to make some sense of that. And of course it will be better if we can get some delayering of this chip. There are also some people asking me for like, oh no, there will be a FPGA replacement. This is not my main objective, but yeah, well, kinda. There's already some people done that already, so they will benefit from a schematic that I'm started on. Oh, by the way, that I can show you. That I can show you. Yeah, so let's see if I can figure this out. Because this is Linux, it's not. We found this cool program, you know, Logisim. That was, I have used it before, I just had forgotten the name of it and why it exists. Logisim is getting outdated. There are some forks about it. Those forks are maybe not doing this some modular or architectural design. Architectural, then I mean like you can have sub-circuits, and then you draw this sub-circuit, like for example this one. If I open it, I have drawn a circuit with inputs and outputs, and then you can store it as a circuit in your top design. So, and the really cool thing about this program, it's called Digital, by the way. I wasn't aware of this. I saw on Twitter that when I posted about this, it was really popular. So, and what I found is that you can export a VHDL, for example. And yeah, now I have some errors, but I will just link in the picture. Alright, so this is from Twitter, and as you can see, this is the circuit, and and then you can export it. It's really cool. I didn't know you can do that. You can probably do that with a top-level design also. It will probably make modules out of that. I don't know. So, but anyway, that's a good tip. You can download it. I will link it in the description below. So, yeah. download and installations. There you can find it. Anyway, so I will use that to draw all the circuits that I found. For example, these are all the address decoders. So, and as you saw in my first video, the way that works is that you have all the address lines, and then you have the read-write signal, and then whenever that condition is met, these taps you saw in the diagram, you will get an output. So, and also what you can do here, you can actually do a play. So you can actually select things like read. You can see now this one is on, or write, and we can change the address to 1, and then this one goes on to 2, and then to 3, and then to 4, and so on. So that's pretty cool. Then you can just verify your circuits on the fly. And I think you can also have a clock element in here. Okay, now, thank you very much for watching. Bye bye.